alkene MCPPA. Converts the alkene to what? Epoxide, yeah, and then the epoxide. So after step one, we have the epoxide. Yeah? Then we come in here with methylamine, good nucleophile, attack which carbon? We can attack and open up the epoxide, which carbon? On the right, open it up. Okay? There's no acid here. We're not protonating the oxygen, but we have what's considered a strong nucleophile. It's not super strong, but amines, primary amines, or tertiary, sp3 nitrogens like this are pretty basic, pretty nucleophilic, and that's going to give what? Attack here, then proton transfer, yeah? Proton transfer. Yeah? Everybody good? Yeah. Nucleophile, carbon, carbon, OH. Yeah? Okay, I'm not doing full mechanism here. I'm basically just showing you product, but I'm thinking mechanistically. Anybody need full mechanism? What you need? This attacks there, right? I'm just going to call the big ring R, right? We get what? This kicks it off, right? Becomes O minus. Two lone pairs, boom, becomes third lone pair. It's no longer bonded here. What's bonded here now? The nitrogen. Nitrogen has two H's and a methyl. That's a positive, right? Gives that. Then what? And what do we call that process? Proton transfer. This is going to take an H from that or another molecule, the H from the nitrogen to another molecule. We did this last time. Basically, we got to take care of the proton. The H plus is going to sit here instead of there, and that gives this. So these two steps, I indicated that here. I wasn't doing full mechanism. We were just showing product. And there you go, right? Instead of two H's on the nitrogen, we only have one. Right? Proton transfer. We did it last time. We'll do it a million times moving forward. Okay? You need to understand what proton transfer is. Some of you do not because you will unfortunately not ever think about it. It's not just you don't know where the lone pair came from, etc., etc. We explained it last time. It's very important to make sure you understand it. Yeah? How we do on this product? Yeah? Pretty straightforward. We just had sort of multi-step. Make the epoxide, then react it with a good nucleophile. Okay. Other strong nucleophile. Anybody have a product down here? What'd you get? Methoxide, SN2. I didn't look completely. We have a strong nucleophile. This is minus, right? And this strong nucleophile will attack where? Least sterically hindered side, kick off the oxygen, and that's going to give, boom, oxygen just gets kicked off. Nothing changes with that stereochemistry. This methyl just gets pushed up, still forward, and the nucleophile is now, the oxygen leaving group is straight up, the new group comes straight down. It doesn't mean I can't have a little bond angle this way, it's still straight down in the plane. So the methoxide, potassium methoxide, as is a nucleophile and kicks off the oxygen. There's no acid here. This is basic conditions. Methoxide is just like hydroxide. It's written backwards. Usually we see KOH. No matter how you write it, it's the same thing in class. Instead of an H, it's got a methyl. It's still O minus, right? Right? Rid of that. Hydroxide, methoxide. Good nucleophile here. And we got to get a proton. There's no proton transfer because there's no proton here that's acidic that can be transferred. Where's the proton going to come from? It could come from methanol. Or you might throw in some acid when you work this reaction up. But to show a neutral product, we can get a proton from methanol, because this is pretty basic. And I'm just going to say final product, okay? Just put an H on your oxygen. I'm not going to redraw the entire structure. Question?
Would the potassium methoxide reform at the end because when you take the proton from methanol?
Yeah, you would, because right here you're remaking methoxide. Yeah, and you can show the potassium with it. You can show it like that, or you can just show it MEOK or whatever. Yeah. So actually, we're just adding methanol to the epoxide. So actually, the potassium methoxide is a catalyst here, where it's going to be regenerated, right? They're regenerating the methoxide right here when this takes an H. Yeah.
For the way that the O-methyl attacks, does it have to be drawn the way you have it? Like when I did it flip, so the O-methyl was on the top and then the methyl was just on the bottom. Does that make any difference?
What do you mean?
Like my right side of it is this, the same, but then yeah, those two on the left were just.
You got it bolted down?
Yeah.
Well, no, you got to have inversion.
Okay.
Inversion. Leaving group straight up, how does the nucleophile come in? Straight down, right? This is like this. This methyl is forward, but it's a little down. And the nucleophile comes in straight up, and oxygen's like that, boom, boom, bonded back over there. Straight up, kick off the oxygen. But when this comes in, the methyl goes like this to make room. That's the inversion. It's still forward, but now it is up and forward. Again, you can do R&S. We've done this several times, and we introduced it in Organic 1. And I suggested you pull out that handout where I showed you all this for the very first time. Anybody else wants that handout, please let me know. I gave you a handout, 2 ways to make nucleophile carbon bonds. One was adding a carbocation. One was adding to a carbon and kicking off a leaving group. Back in September, October, late September probably. Okay. Is that a good leaving group? Oxygen? Usually not. Why is it leaving here? Because it's an epoxide. Strain 3-member ring, it will leave. That's what we have now seen, yeah? Oxide oxygen will leave. You do not have to have acid. As long as you have a strong nucleophile. That's what we got in these cases. Strong nucleophile. We said sp3 nitrogens can be strong nucleophiles. Ammonia, strong nucleophiles. Grignard reagents, strong nucleophiles. Okay, alkyl lithium, strong nucleophiles. No acid. No acid required.
If you added heat to that, would it just bust open
I'm about
and
to
make
tell
a
a joke,
tertiary?
but go ahead.
And just make a tertiary carbocation on my right hand side?
Hold on
There
now,
was heat.
hold on now. This one up here? We
Yeah,
just did?
right, if there was heat there, would it bust open just by
No.
itself?
No, we said last time. We'll say it again. Is this SN1 or SN2?
That does one too.
We said on the handout, doesn't it say with strong nucleophiles, always SN2?
Okay.
So you're saying bust open and make carbocation?
If you added heat, I just wondered
No.
if there was heat involved, if it would just open up.
No, no. Strong nucleophile, always SN2. Okay? You're suggesting just open up and make carbocation.
Right.
Like an SN1, carbocation type chemistry. No.
Mhm.
Strong nucleophile, always SN2. Because for the oxygen to leave like that, it got to be protonated. Okay? And since under basic conditions there's no proton, there's no acid, you're never going to do that.
Okay.
At least not in this class. Okay? To get the oxygen to just leave on its own, you got to protonate it. The difference is if you have a strong nucleophile, it'll come in here and kick that oxygen off even without protonating it. We're breaking that rule that we learned in Organic 1 or whatnot. Okay? To get carbocation chemistry with epoxides, you need acid. Okay, this is just a comment below. For example, the reaction we did with this epoxide was regioselective. The nucleophile attacked over here, selectively, this region. Yeah. It was also, this reaction is also stereoselective. As we get precise stereochemistry, but basically terminology that we saw in Organic 1. Okay, this brings us to a big topic for Organic 2, that is multi-step synthesis. And we'll look at it here, and we'll do more going forward. Okay, use of epoxides in multi-step synthesis, a great source of 2 carbons, and we can get nucleophile carbon-carbon OH. Retrosynthetic analysis, need to look at that. Here's an example. Starting with an alkene, provide a synthesis of terbutaline, drug used to treat premature labor in women. Over here, terbutaline. Can be made using an epoxide reaction. Keep in mind nucleophile carbon-carbon OH. Do you see a nucleophile carbon-carbon OH in this molecule?
Yes.
What do you see? The amine carbon-carbon OH? Yes. That could be a nucleophile, nitrogen nucleophile attacking the carbon, carbon-carbon OH. And so this can go back to, retrosynthetically, that epoxide plus what? Plus that primary amine. Yeah? So, coming forward, would these two react to give that? Right? Nucleophile attacks which carbon? On the left or right? On the right, least stirred and hindered. Kick off the oxygen. And then what next step after that? Proton transfer. That would give that product. So we can think backwards. What can I use to make this? Okay, going backwards. Epoxides are very versatile, very reactive, lots of nucleophiles. Ultimately, to give what in the structure? Nucleophile, carbon-carbon OH. Okay? Let's go ahead and flip over and do a couple. Lots of miscellaneous applications here. I give you a few here. Sometimes we may have time to look at these, sometimes not. You can look at them on your own. Just some interesting and maybe okay, here's the compound that's discussed on this handout. Show a synthesis of it starting with this. I actually give you something to start with. Can you convert that this is going backwards. I said, okay, I'm going to go backwards to this. Going forwards, I'm starting with this. Can you start with this and get to the compound of interest? What would you do here? Well, be careful. I wouldn't start over there. If I told you to start with carbon and make this, I wouldn't go over to carbon and start there. Go backwards, retrosynthesis. Let's go backwards and see if we can get back to that over there. One step at a time backwards. Much easier. Trust me if you want my recommendation. And I'm telling you what I'm going to be doing. So, and when you go backwards, you're kind of like breaking the molecule apart. What reaction? Okay, you want to get the smaller molecules off of it. Clearly, if we look over here, no chemistry is really going on over here. It's all the same. Chemistry needs to take place sort of over here. What can we do over here going backwards? You just give me one reaction. What one reaction can you do to give this?
To give?
What one reaction can you do to give that? Well, one entire reaction. Proton transfer is just a step in a mechanism.
The oxide.
Reacting with what? It's almost the same moves that over there, right? Okay. I'm not going to draw out the full structure here, but if it had epoxide, we'll cut that off. If it had epoxide here, like this, and react this with isopropylamine. Okay, you can draw this, you can look at it. Epoxide here, isopropylamine, we come in here, attack that carbon, kick off the oxygen proton transfer. Would give that molecule. So basically, I can go back to the epoxide. Because coming forward, I can just do that. So there's one reaction. The epoxide reacts with amine, we'll give that. One reaction, yes. Now let's take another step back. And eventually, let's get to where we want to start to. Okay? Basically, how can you make this? There you go. Well, how can you make this?
From an alkene.
How do you typically make epoxides?
From alkene.
From alkenes, right? So let's go back to, okay, again, let's go back to the alkene. Because if you had the alkene, could you then make the epoxide? Yes. Well, you can make the epoxide by reacting it with MCPBA. So now we have two steps, because you know if I had the alkene, I can convert it to the epoxide, then I can convert it to that. Well, how do you want to make it alkene?
From an alcohol and dehydration.
Can you make an alkene from that over there?
No.
Yes. What would you react that with? You actually make it from that. What do you want to react that with to make the alkene? What type of mechanism you want to do? I would react it with maybe potassium terbutoxide, which is a common base used to do what type of mechanism? E2. Okay. And there you go. We worked our way back to where we were asked to start at. In a few weeks, I may come back to that and go back even further. Okay? Once we learn new chemistry. So in the end, how would you make that from this? We worked backwards, and now we know we take this and do a E2 elimination, put it into a double bond, convert the double bond to the epoxide, react the epoxide with isopropylamine, and open it up. There you go. Have a three-step synthesis. We analyzed that. We arrived at that by doing a retrosynthetic analysis. Let's try some other multi-step syntheses. For photosynthesis of this compound, starting with bromobenzene. Okay, bromobenzene. There we go. We don't want to stare at bromobenzene and say, what can we do, what can we do? We know where we want to eventually start from, but at that point, let's come back over here and ask one question. Let's just go back one step. That is, what reaction could you do to give that product? What chemistry do you know to give that product? The main functional group there is a carboxylic acid. Do you know any reactions that we give with carboxylic acid? And this is where it comes in, knowing your reactions. I think it was on the quiz, right? Oxidation of the primary alcohol gives, okay? So take this back to what? To that primary alcohol? 2 carbons. Benzene ring, 2 carbons, okay? Is that reasonable to go back to that? That is, if we were here, could you come forward to give that? What would you use? One of the big 3? Okay. Like maybe chromium trioxide and acetic acid or something. Would that give that? Okay. You can only use reactions you know. And the only reaction you know right now to make a carboxylic acid, I believe, is oxidation of a primary alcohol. So this is where you have to catalog your reactions. You know, this becomes your reaction toolbox. No carbs, functional group transformations. Okay? Quick, how do you make an alkene? E2 elimination is one way. Do you know any other ways? You can sit down one way and come up with every way you know to make an alkene. Okay? How do you make alcohols? Do you know any ways to make alcohols? Et cetera, et cetera. This is a lot what organic chemistry is. And when you do multi-step synthesis, you need to know that. Okay? The more you know that, the more you're going to be able to quickly do, and you have choices. Now down the road, we may know 3 different ways to make carboxylic acids. And you can show 3 different retro routes. And then you decide which one you like best. At this point, I only know 1 for you guys. And that's going back to primary alcohol. Now, we know if we had this, we can make product. Now the question becomes, how do you make this? How do you want to make this? Keep in mind that we got to come from just benzene, carbon-carbon OH. I identified a carbon-carbon OH, which is very important because if you can identify that, you know you can do an epoxide reaction. Anybody seeing what you might do here? At some point, your retrosynthesis has to just kind of nudge into sort of opposite. Okay, I see how to come forward now. Nucleophile, carbon-carbon OH. Could this be a nucleophile in some type of reaction? Yes. Yeah. We could take this back to this epoxide. That is the oxygen bonded here, 2-carbon epoxide plus what? Phenyl what? Need anion. But what's the most common form here for carbon anion? Carbanion. Phenyl, right? We need this to be a nucleophile to attack here, but it's Grignard. Phenyl magnesium bromide equals what? When you see that, what do you really see? You see this, right? Okay, it's all in your notes, guys. I'm not going to review it, okay? I'm not going to restate it. All right, we covered Grignards. You know what Grignards are. This is essentially what? And essentially that. And if you had that, tack here, keep it open. Okay. These two react to give this. What would you need here when these react? You've got to have what? After these react, what do you got to do? You can say hydrated. I would rather say protonated. You got to have appropriate workup. H plus workup. Okay. So if we can make this by reaction of this simple epoxide with phenyl magnesium bromide. Okay. This said starting with bromobenzene. Can you take one of these back to bromobenzene? Yeah. I mean, how do you make this? You take bromobenzene and you react it with what? Magnesium metal. Make the Grignard. So there you go. Your answer would be, I know how to make that from bromobenzene. I would first treat it with magnesium to make the Grignard. I would then react the Grignard with ethylene oxide, the simplest epoxide, and upon H plus workup, that would give that alcohol. And then that alcohol I can oxidize to the desired product with one of the big three. And the direction said start with this, and I did. It didn't say you had to make everything else. As long as you start with this, I just brought that in. Maybe I bought it, okay, or whatnot. Everything else you can just use, as long as you start with this. Okay, there's others for you to try here. Down below, those say starting with styrene. All right. to our board, but it will not erase. These markers. I don't understand that. I've been using these markers for 10 years and they're not erasing well anymore. Okay, there's a puzzle for epoxides for some practice. You remember in Organic 1, I gave you a puzzle for like this on alkene reactions. Okay, here's another one that you can do. Has a little riddle. Was the sodium atom certain that he had lost an electron? Maybe it was a she. And to get the answer, you fill in down below. Each number has an answer shown over there with a letter. For example, this number 8, you find the answer, and maybe the answer is T. And so you would put a T here for 8. By doing all that, you get the answer to the little riddle. And one of them has been answered for you, number 10. I don't know why they answered that for you, maybe just to illustrate something. So there's some questions for practice. You know, you can look at these things. These are all nice examples of stuff. Again, lots of applications in epoxides. Epoxides are occasionally seen in biochemistry. Aflatoxin B1 is one of the most toxic compounds known to man, particularly in causing cancer. Okay? It's formed by a fungal organism. Okay? Penicillin is formed by a fungal organism. Penicillin is a good compound, very helpful to mankind, right? Okay? This compound formed by some fungi, bad compound. Okay? And the way it's bad is this alkene right here is converted to an epoxide in the body. Okay? It's an oxidation. Okay? And then this epoxide, very reactive, electrophilic, and proteins in your liver start reacting there. The proteins have amino groups, and it leads to liver damage and ultimately liver cancer. Okay? All right? Luckily, your body has a sacrificial nucleophile, glutathione. It has an SH group, very nucleophilic, and it may be in the anion form in certain conditions. But this protects your body because it will react here instead of your proteins, and you get a product that looks like this, sulfur nebula, but because it's very ionic with all these carboxylate groups, this can be eliminated from the body pretty easily because your body's aqueous. Okay. And this is an elimination, detoxification type mechanism. The problem is your body only has a certain amount of glutathione. And if you get too much of this around, you'll run out of glutathione, and then your proteins start reacting, and then you got bad trouble. So glutathione can only do so much for you. Okay? This compound was mainly first discovered back in the 1960s because turkeys over in England, turkey farms were dying, like all of them were dying. And it turns out that the feed that they were eating, it was a peanut-based feed, and the feed had become moldy. And the moldy feed was being distributed throughout the region. And the turkeys were eating moldy feed, but the mold was producing this compound. And it was causing bad, acute liver damage, and the turkeys were just dying. It was like the farmer was like, all my turkeys just died last week. Okay? But molecular chemist, whatnot, determined this compound and structure. How did they determine structure? A lot of work, but NMR was very helpful in determining structure. Mass spec, IR. Okay, a lot of other things there. Okay, one last thing to show you before we leave here is blood clotting. Vitamin K. I can show this next week as well. Let me add this. Oxidation of alkenes is our next topic. I'm going to send you that handout by email so you can get looking at that before next Wednesday. But next Wednesday we're going to have to start pulling things together, including NMR. Okay? And once I start going through NMR, if you haven't done a good amount of review, it's just going to be a waste of your time. Okay? Please be ready for NMR next Wednesday. And our next topic, alkene oxidations.
Are we done?